Okay, this is the second part of going over a few questions we did for directed study. I'm sorry, the first part ended abruptly. We did this question in a more efficient but slightly unusual way, where we had an inclined plane, and it was found to be better to resolve horizontally and vertically, which is often rarely the case. Here it was the case because we had a horizontal force and no other forces, so it actually worked out better that way. It's not that bad if you do resolve parallel and perpendicular, so I think I better do it that way too. So it's the same question with different, the way I'm going to draw my diagram is going to look a bit different because I'm resolving in a different direction, but same question. So let's draw the forces in. We've got a reaction force, we've got a weight, and we got the friction because it's on the point of moving down a slope, which is a third r, and 0.4 g. We got r here. So we're going to stick with the more conventional way of doing these things, resolving horizontal, parallel and perpendicular to the plane. So this angle here is alpha, and this angle here is also alpha, and those are the two ones we're going to resolve into two different directions. The weight, if we resolve that bit, that will be 0.4 g cos alpha because it's next to the actual force where I've marked the angle. And this component of the force here, because it's away from that, that's 0.4 g sine alpha. Okay, so now we're going to resolve this force. Maybe change colour. Let's go to green. There's a component up the slope, and there's a component into the slope like this, always going in the same direction as this arrow, because the arrows have to point to the same point. So we're going to resolve these in the two directions. This one here is P cos alpha, and this one here is P sine alpha for the same reason as before. We've marked the angle there, so that one's cos, it's next to that angle, and this one's away from, we haven't marked this angle, so we've marked that angle, so it's P sine alpha that we're working with. Okay, so let's set up our equations. We're going to resolve, let's resolve perpendicular to the plane first of all, because forces, it's definitely not moving in any direction, in fact, so it's definitely all balanced in that direction too. Well, forces upwards are R, obviously, but both the other two forces, this P sine alpha there and the component of the weight, are acting in this direction, whereas the reaction is going upwards to the left. Reactions in that direction. So that's what's going to balance out. We're going to have R equals to P sine alpha plus 0.4 g cos alpha. Now we have sine alpha and cos alpha here. Sine alpha is 3 over 5 and cos alpha is 4 over 5. So let's sub those in. Sine alpha is 3 over 5 and cos alpha is 4 over 5. But the problem is, and it's kind of obvious really, when we resolved vertically there, we only had R in our formula, whereas here we've got an R and a P in our formula, so we can't really do anything directly with that. So we're going to leave that one as is for the moment. Now let's resolve parallel. It's not moving in that direction either. So we can say any forces in this direction are going to be balanced by forces in this direction. So forces upwards, obviously it's the P cos alpha. And the forces downwards are the component of the weight, 0.4 g sine alpha. And also the other force, which is the friction which are marked as null now, which is 1/3 r. Okay, let's sub in my ratios for sine alpha and cos alpha. Sine alpha is 3/5, cos alpha is 4/5. Now, I'm going to times this through by 15. The reason is I'm going to get some, I know that I'm going to end up subbing my r into here, and it's going to get all really very messy and untidy with lots of fractions involved. So I'm going to try and tidy that up and avoid using a calculator as well. Often if you're happy, if you do it this way, it's going to be more accurate. Times by 15 because I've got 3's and 5's on the bottom of my fractions, so that'll get rid of them all. The lowest common multiple of those. So times this by 15, well, basically that's the same as times in the top bit by 3, so that's 12p. Times in this by 15, we will end up with the 5 cancels, that'll be 9, that'll be 3.6g, and times this by 15 here, and that will obviously be 5r. Okay, so I'm going to sub in my value of r now. So this value of r is going to go into there. So substitute for r. You can see this is longer than the original version. Substitute for r. We have 12p equals to 3.6g plus 5 times by 3/5p plus 0.4g times 4/5. Okay, so I have 12p equals 3.6g. If I'm timesing this by 5, I'll end up with 3p there, and timesing that by 5, the 5's will cancel, and I will have 1.6g for this term here. Okay, so taking the p to the other side, I have 9p equals to 5.2g. Let's write 5.2 as a fraction, 52/10 or 26/5g. So that means 9p is equal to 26/45p. Okay. Now, as I said before, that's okay to leave the answer like that in exact with g in it. If we give 2 or 3 significant figures, that's the other alternative. I'm going to give 3 here, 5.66 newtons. Okay. What we notice here is, because of the way it's gone about and we've done it, so clearly the examiners anticipated doing it the way we did it before in the previous video, horizontally and vertically, because we've actually answered part B. So that's part B before part A. And so then what happens is now we can go and substitute our value of P back into this formula here to work out R. So that gives us that R equals 3/5p plus 0.4g 4/5. I've just rewritten the formula, haven't I? Anyway, 3/5 times by 26/45p. Oh, that should be g there, shouldn't it? Of course. Okay, and plus 4/5, which is 2/5g times 4/5, and that actually breaks down to, it doesn't look particularly promising, but it does when we work it out. The 45 there cancels 15. That works out 26 over 75g plus 8g over 25. And that equals to 24 plus 50g over 75. I'm just avoiding using the calculator, which is our 2/3 of g, which we worked out before, which comes to the 6.53 newtons that we did before. So I think you'll agree that although it's possible, it was easier to do horizontally and vertically. Unusual case where it is easier to do horizontal and vertical, but we've got an inclined plane. So there we got it. It did get done, but a little bit longer. So that whole work there, let's have a look at what the question was actually. Out of 10 marks, so there we got 10 marks for this original version that we did, where we did it horizontal and vertical, and for the same 10 marks, of course, more chances of errors creeping in as well. The perpendicular and parallel bit, that's that bit there, same for the same number of marks, and a little bit more time spent on it as well. So there we go. Let's do question 3 from the directed study. This is a smooth plane this time, so at least we don't have to worry about that. And it says, so that the angle is a third if it's in equilibrium, because it's been held by this one force upwards. Okay, so we've got reaction force here. And we've got weight going downwards, which is 6g. Okay, let's just resolve the forces. Now we are going to go parallel and perpendicular, as we almost always do with these cases. It says, so that cos theta equals to a third, and find the normal reaction force. Well, if we resolve parallel to the plane, forces up are going to be equal to forces down. So resolve parallel to the plane, we have forces in this direction must be balanced, so we have, and in this direction must also be balanced, parallel in that direction. Right, well, let's resolve the forces then. We've got the weight has got a component in this direction and this direction of 6g cos 30 because it's next to that marked arc, and 6g sine 30 because it's away from that marked arc. And then the 49 force got a component upwards of 49 cos theta because it's next to that marked arc, and also a component into the plane there of 49 sine theta for, not 4g sine theta, 49 sine theta for the component there. So going in this direction, there's only two forces at play, these two here. Okay, so let's do that. So they must balance. That gives me the force downwards, this one, 6g sine 30 must be equal to the force upwards, this one, which is 49 cos theta. Now sine theta equals a half, and g is 9.8, so 6 times 9.8 times by a half is equal to 49 cos theta. Sorry, I don't want to be using my calculator again. So that's 49 over 5 is 9.8 as half, and that equals to 49 cos theta. So the 49 cancels. Okay, the 49 cancels like that. And so we have cos theta equals to 6 over 10, which is 3 over 5 as required. So I said it was a third, but actually looking at that, it must have said 3/5. Okay, rather than a third. Okay, so that's the first part of the question. That's part A done. Now, to find a normal contact force in part B, we're just resolving perpendicularly. And we've got forces upwards, which is R, in that direction, must balance with two forces, which is the component of the 49 Newton force. So that's 49 sine theta. And also the 6G cos 30 force there. Okay, but we know that sine theta, we know that cos theta is 3/5, so sine theta, if you work it out, is 4/5. You can work that out easily enough. So we can sub those numbers into our formula there. Let's write it, 49 sine theta, which is 4/5, plus 6G cos 30, and that gives us an answer to three significant figures of 90.1 newtons. Okay, so that's part B done. So part C is the genuine dynamics bit of the question, because it's starting to move. We've got a different situation really. We've got this 49 Newton force is now applied horizontally. We've still got the weight. We've got a reaction, but we don't actually need the reaction force here because there's no friction. Okay, there is a reaction force, but we don't need it. It will have changed from before, by the way, because of the change in 49 newtons, but we're not really interested in that reaction force because we don't need it because it's a smooth plane. And then we've got the angle here, 30 degrees. We really don't only need to look at the component of the weight that's down the slope here. So that's 6G sine 30. It will start to accelerate up the plane as a result of this force here, which is our 49 Newton force. So if we apply F equals ma, force is up of 49 newtons. Okay, and wait a minute, have I misread it? It's now applied horizontally. So wait a minute, that's wrong. Do apologise. It's applied horizontally. So actually, this force does have a component there. That's 30 degrees. And this component here, therefore, is 49 cos 30. So, right, okay, never mind. Noticed in time. So we've got 49 cos 30 equals, oh no, it doesn't equal anything. 49 cos 30, take away the component of the weight, which is the 6G sine 30, is equal to the mass, which is 6 times by this acceleration. And if you work that out, that gives us an acceleration of 2.17 to three significant figures. So we're either writing 2.17 or we're writing 2.2 for that question. So that's the three questions done from the directed study sheet that we did. Perhaps harder than I'd realised. And this question's all right. But question 2, if we did in the standard way we normally do these, is quite long. So that's why I've made this video, or these two videos. So that's that. Hope that was helpful. Okay, goodbye.